Hi there, this is Theodore, and in this video we're going to alter our current model code to support hyperparameter search. This is a common task in all machine learning models. The current model code has got the DNN hidden units hard-coded to be 100, 70, 50, 25. We want to expand our model to be able to accept and explore a wider range of hyperparameters. TFX uses the Keras Tuner library to do that. Keras Tuner provides an API to declare our hyperparameter search space and some tuner classes to select the best combination inside the search space. Usually the hyperparameter space is huge and you can't afford to run a full training iteration for each one of the points inside that space. The technique that's often used is just to run fewer training steps for each hyperparameter combination and see which one converges the best. The tuning technique we will use in this video is called Hyperband. It's a very nice paper that I recommend you read afterwards. Essentially, the tuner evaluates each hyperparameter combination with a bandit approach. It resembles a sports tournament-like selection, with brackets iteratively selecting the best performers. Let's get coding. It's pretty simple. The tuner component detects and runs a function called tunerFn, similarly to our train function. This is responsible to build our hypermodel through Keras Tuner and provide the hyperparameter space. The artifact for this component is a simple txt file that contains our search space and the best hyperparameters that were selected, along with a metric value that they maximized or minimized. The artifact maps directly to a Keras Tuner.hyperparameters object. As usual, declare the component and add it to the component list. Notice that I place it before the trainer component. This is because the trainer will actually use the produced hyperparameters to perform the full training of the model. Just wire the outputs of the training component to accept the best hyperparameter configuration from the tuner. At this point, you can optionally swap this with an importer node, just as you would with a user-specified schema artifact. Alternatively, just provide sensible defaults in the training function if the provided hyperparameters are none. Moving on to the model code, the first step is to refactor our model building code to accept a set of hyperparameters as the sole input value. This means changing our build Keras model function and also using the hyperparameters on our trainer's run event. Let's just use some constant for our DNN hidden unit hyperparameter names, and also change the build Keras model function to accept this as an object. Don't forget to read the new hyperparameters and pass to the model in our training function. For the tuning part, we need to declare two things. First, a small function that just declares our search space and returns the object. Read more on the hyperparameter space construction on the Keras Tuner documentation page. Secondly, the actual tuning function. This one should set up our tuner along with the training and evaluation inputs. Its inputs are similar to the training function. A fnargs object instance, it just returns a tunerFn result. This result contains the tuner instance, the training and validation sets, as well as the training and validation step count. Pretty straightforward. Here is some of the tuner output, and it's our readable best hyperparameters.txt file as an artifact. Notice that there is some .temp directory as well. Those are the Keras Tuner logs. Keras Tuner creates one directory for each training run. You can visualize them with TensorBoard exactly like the last video by just changing the log directory path. That's all that's needed for hyperparameter tuning. In the next one, we're going to take the last step in order to deploy the model to production. Thanks for watching and see you in the next video.